Ever tried to clean up a messy calendar with overlapping meetings? Merge Intervals is a Pattern Mastery 100 classic and a go-to at Google, Amazon, and Meta for interval manipulation and sorting skills. More than 30% of candidates miss subtle merge cases or get tangled in the logic. Master this, and you'll be set for any range, timeline, or schedule question. Let's break down merge intervals with the basic approach, so you can handle any overlap or merging scenario with confidence. Given an array of intervals where each interval is start, end, merge all overlapping intervals and return an array of the non-overlapping intervals that cover all the input. List of intervals, unsorted, may overlap. List of merged intervals, sorted, non-overlapping. Think of merging meeting times on a shared calendar so no one gets double booked. Interviewers might ask, how would you efficiently compress overlapping bookings or busy periods? What's tricky? Input intervals may be unordered. Overlaps may cascade. Merging two can create new overlaps. Sorting first is essential. Sort intervals by start time. Initialize a result list with the first interval. For each interval, if it overlaps with the last in result, start less than or equal to end, merge, update end to max current end, new end. If it doesn't overlap, add it as a new interval to result. Let's clarify. Always compare current intervals start with last result intervals end. Only merge when there is overlap. Edge cases. Intervals already non-overlapping. All intervals overlap into one. Empty input. Sort intervals by their start value. Initialize the merged result with the first interval. For each interval from the second onwards. If interval.start less than equals last.end, merge, update last's end. Else, append interval to result. Return the result. Sort the list. Single pass through intervals for merging. Let's try to implement it using solution 1. Time complexity, O(n) log n. The concept discussion. The goal is to combine overlapping intervals so the final list has no overlaps. The easiest way to do that is to sort by start time first. Once intervals are sorted, any overlaps must happen between neighbors. Then we scan from left to right. If the current interval doesn't overlap the last merged one, we append it. If it does overlap, we stretch the last merged interval's end to cover the bigger endpoint. By the time we finish, the merged list is clean and minimal. This function sorts intervals by start time, then merges overlaps in a single left-to-right pass. First, we sort the intervals by their start values. This is the key setup step, because after sorting, overlaps become easy to detect. Only the interval right next to you can overlap with you in a meaningful way. We create a merged array that will hold the final, cleaned-up intervals after we combine all overlaps. Now we iterate through the sorted intervals. There are two cases. No overlap. If merged is empty, or the current interval starts after the last merged interval ends, we add it as a new separate interval. Overlap. If the current interval starts before or at the last merged end, they overlap, so we merge by updating the last merged end to the maximum of both ends. Once the scan completes, merged is the final list with all overlapping ranges combined, so we return it. And that's how this algorithm works. It first sorts the intervals by start time to line up potential overlaps, then it scans once and either appends a non-overlapping interval or merges by extending the previous interval's end. Efficient, simple, and elegant. Let's test our function with this list of intervals: 1, 3, 2, 6, 8, 10, 15, 18. Each pair is a range, and our goal is to merge any ranges that overlap so we end up with the simplest non-overlapping set. First, the code sorts intervals by their start value. In this case, they're already in order, so the list stays the same. Now we scan through them and build a merged list. Start with 1, 3, in merged. Next is 2, 6. Since 2 is within the previous interval's end, 3, they overlap. So we merge them into 1, 6, by extending the end to the max of 3 and 6. Next is 8, 10. This does not overlap with 1, 6, because 8 is greater than 6, so we add it as a new interval. Next is 15, 18. Also no overlap with 8, 10, so we add it as well. And that's exactly what our program outputs. 1, 6, 8, 10, 15, 18, matching the expected result. The output makes perfect sense because 1, 3, and 2, 6, overlap and combine into 1, 6, while the intervals 8, 10, and 15, 18, are already separated. So, our implementation is correct. The algorithm sorts once and merges in a single pass, efficient and accurate. Let's try to implement it using solution 2. Time complexity, O(n) log n. The concept discussion. This version is the same merging idea, but we store the merged intervals in a stack. After sorting by start time, we scan left to right. The top of the stack represents the most recent merged interval. If the next interval doesn't overlap with the top, we push it. If it does overlap, we merge by extending the top interval's end. In the end, the stack already contains the final merged intervals. This function sorts intervals, then uses a stack where the top always holds the latest merged interval. First we sort by start time. This guarantees that any overlap will happen with the most recently processed interval, which makes a stack-based merge natural. We create a stack to hold merged intervals. The last item in the stack is the one we compare against, because it represents the latest merged range. Now we scan through intervals. 2 outcomes. No overlap. If the stack is empty, or the current interval starts after the top interval ends, it's a separate block, so we push it onto the stack. Overlap. Otherwise, it overlaps the top interval, so we merge by updating the top interval's end to the larger end value. After the loop finishes, the stack contains the fully merged intervals in order, so we return it. And that's how this algorithm works. It first sorts the intervals by start time, then it uses a stack to either push non-overlapping intervals or merge overlaps by extending the end of the top interval. Efficient, simple, and elegant. Let's test our function using this input, 1, 4, 4, 5. These are time ranges on a number line, and we want to merge anything that overlaps, including intervals that touch at the boundary. First, we sort by start time. Here it's already sorted, 1, 4, 4, 5. Now we scan through and use a stack to build the merged result. We push 1, 4 onto the stack first. Next we look at 4, 5. Its start is 4, and the end of the last stacked interval is also 4. Since the condition for a new interval is interval 0, greater than last end, and here 4 is not greater than 4, these two intervals are treated as overlapping/touching, so we merge them. We update the end to the max of 4 and 5, turning 1, 4 into 1, 5. And that's exactly what our program outputs, 1, 5, matching the expected result. The output makes perfect sense because 1, 4 and 4, 5 connect seamlessly, forming one continuous interval from 1 to 5. So, our implementation is correct. The algorithm sorts once and merges in a single pass using a stack, efficient and accurate. Alright, quick recap to wrap up merge intervals. We're given a list of time ranges, and the goal is to combine any ranges that overlap so the final output becomes a clean set of sorted non-overlapping intervals. In other words, each merged block should end up represented by one clear interval. The key thing to watch is that overlaps can chain, one interval overlaps the next, which overlaps the next, and so on. That's why sorting by start time is the turning point. Once everything is sorted, overlaps become predictable, and only neighbors can overlap. After that, the whole problem reduces to a simple linear sweep. The plan is, sort intervals by start, then start your result with the first interval. For every next interval, compare it to the last merged interval in the result. If there's overlap, extend the end of the last merged interval. If there's no overlap, append the interval as a new block. One pass, and you're done. We sorted once, scanned left to right, compared against only the most recently merged interval, and merged by updating the end boundary when needed. LeetCode ran smoothly with no errors. We confirmed it works on overlapping and non-overlapping inputs, handles boundary touches correctly, supports empty and single interval cases, and all test cases passed. The takeaway is, sort first, then merge as you sweep. Keep one active interval and expand it when needed. This pattern shows up everywhere in interval problems, and once it clicks, it starts feeling automatic.